Hello, Matthews, Gatos here. In this lesson, Chapter 5, Lesson 3, we are going to look at how to evaluate logarithms. So in the last lesson we looked at two different graphs. We looked at y equals 2 to the x, for example, and a graph of y equals log base 2 of x. So let's look at 2 points that are on those graphs. So on the exponential graph, the point 3 and 8 is on the graph. So what that really means is substituting this in for x and this in for y. If it's on the graph, it means it satisfies the equation. So that means that 8 is equal to 2 cubed. And we know that that's true. We saw that point, if I turn it around, flip it around, 8 and 3 was on the graph of y equals log base 2 of x. So again, substituting this in for x, substituting this in for y, that means that 3 equals log base 2 of 8. So those are the same points on two different graphs. What that tells us is that 8 equals 2 cubed is equivalent to saying 3 equals log base 2 of 8. It means the same thing. So in general, y equals b to the x is equivalent to x equals log base b of y, meaning the basis is the same, x and y interchange, and that's again because exponential and logarithmic graphs are inverses of one another. So we're going to take this idea and try and use it to evaluate logs. So, for example, we have this detailed solution. We're just going to go through it together. We want to evaluate what log base 2 of 8 is without using technology. So what we're going to do is, since we don't know what it's equal to, we're going to make it equal to a variable. So you could choose any variable at all. So Kelsey did this question. She chose the variable v. So log base 2 of 8, we don't know what it is, so we're going to make it equal to 8. Then in the next step, she switches to exponential, and she does that using a circle of logs. So base to the answer equals the argument. So 2 to the exponent of v equals 8. In the next step, what she does is write the bases with the same base. So I'm looking for powers of 2. So I see that 2 cubed is the same as 8, so I can replace 8 with 2 cubed. Then I make like a DJ and drop the base since it's the same on both sides. And therefore, v must equal 3. So that tells me that log base 2 of 8 equals 3. So the value of a log is actually the exponent in an exponential equation. So instead of doing all of those steps, what I could do is just ask myself, 2 to what exponent gives me 8? Well, you see through this example that 2 cubed equals 8, and that was the answer, the exponent of 3. So let's use that strategy in a couple other questions. So log base 3 of 81. To solve this, I'm going to say 3 to what exponent gives me 81. So I'm going to go to my powers of 3, and I see that 3 to the exponent of 4 equals to 81. So that means that log base 3 of 81 is 4. Okay, over here, log base 4 of 64. You ask yourself, 4 to what exponent is 64? So if you know the answer already, that's great. You can just put it in. Otherwise, your calculator can help you. Here's my powers of 4, and I see that 4 cubed is 64. So since 4 cubed is 64, log base 4 of 64 is 3. Okay, let's try another one. Log base 7 of 7. So you ask yourself, 7 to what exponent is 7? So hopefully you don't need the table of values for that, but just in case, there they are. So you can see that 7 to the exponent of 1 is 7. So log base 7 of 7 is 1. Now, this is actually a special log rule that we should probably note. This is called the matching law. So anytime the base and the argument are the same number, the answer, the value, will always be 1. Okay, here's another special one we're going to look at. 12, log base 12 of 1. So this is saying 12 to what exponent is 1. So hopefully you remember that 0 exponent from 10C, but if you don't, there it is. So 12 to the 0 equals 1, which tells me log base 12 of 1 is 0. Now this is another special law that we want to take note of, and this is the 0 exponent. So anytime we have an argument that has a value of 1, so anytime the argument is 1, the value of the log will always be 0. because any base to the exponent of 0 will equal to 1. So those are worth noting. So once again, these examples show the value of a log is the power the base has to be raised to equal the argument. So let's try some other ones here. If I have log base b of 1, this is saying b to what exponent is 1. So I know that b to the 0 is 1, so the value is 0. So this is our special law. If I have log base b of b, remember that's that matching law we just went through, and the matching law says if the base and the argument are the same, the log has a value of 1. Okay, so again, there they are, matching law, 0 law. Make sure you have those written down in your notes. Okay, let's try some other ones here. So if I want to evaluate 2 times log base 8 of 512, I'm going to start with the log first. So 8 to what exponent is 512? So if I look at that, I'm going to, oh, there it is over there, sorry. I'm going to look at my powers of 8. So powers of 8, I can see that 8 cubed is 512. So that means that log base 8 of 512 is 3. So then I just do 2 times that log. So I know that the log is 3. So this is really 2 times 3, which is 6. And then I can check that on my calculator. 2 times log base 8 of 512 is equal to 6. Okay, let's try another one. So log base 2 of 1 over 32. So we're asking ourselves 2 to what exponent is 1 over 32. So hopefully you remember this from before. Anytime we have a base that is a whole number and an argument that is a fraction, the value must be negative. So we went over those when we were doing exponent laws. Okay, so let's start first of all, not 2 to what exponent gives me 1 over 32. Let's just look at 2 to what exponent gives me 32. So here's my powers of 2. So I know that 2 exponent 5 is 32. But since the answer is a fraction, I know that my exponent has to be a negative. So 2 to the negative 5 equals 1 over 32. And I know that because when I have a negative exponent, if I were just to be given this question to evaluate, I would take the reciprocal of the base raised to the positive exponent, and then I would get 1 over 32. So instead of doing all those steps, anytime you have a whole number base and a fraction answer, the exponent will be negative. Vice versa, if you have a fraction base and a whole number answer, the exponent will also be a negative. So this tells me that log base 2 of 1 over 32 is just negative 5. And again, I can put that into my calculator to check to see if it's right. Okay, let's try another one. So log base 5 of the square root of 125. So first thing that I'm going to do is take the square root. It's really the same as raising it to an exponent of a half. So I'm going to ask myself, first of all, I'm going to focus on the 5 and the 125. So 5 to what exponent is 125? So here's my powers of 5. And I can see that 5 cubed is 125. So since I want a square root, I have to raise it to the half. So it's going to be 3 halves. 3 because I'm cubing it, half because I'm taking the square root. So that means that log base 5 of the root of 125 is 3 halves. And again, I can put that into my calculator to see that I'm right. And 3 halves, it has a decimal value of 1.5. Okay, let's keep going here. So log base a third of 27. Again, since the base is a fraction and the argument is a whole number, the value must be negative. So I'm not going to focus on the 1/3, I'm going to focus on the 3. So I'm going to say 3 to what exponent is 27? So I can go to my powers of 3, and I know that's 3. So 3 cubed equals 27. So since they are different values, fraction, whole number, I know that it has to be to the negative 3. And again, you can check that on the side. If I were to ask you just to evaluate this, when you have a negative exponent, you take the reciprocal of the base and raise it to the positive exponent, and then you would get 27 over 1, which is just 27. So I know I did that correctly. Okay. Another way I can check to see if I did it correctly is just to put it in my calculator, and I see I do get negative 3. Okay, for this one here, so 4 to the exponent of log base 4 of 16. So what I'm going to do is I'm going to focus on my exponent and then simplify from there. So log base 4 of 16, I'm going to ask myself, 4 to what exponent gives me 16? So if you don't know what that is, you can always go to your calculator. There's my powers of 4, and I know that 4 squared is 16. So that means that log base 4 of 16 is 2. So now I can replace my exponent, which was a log, just with the number 2. So since log base 4 of 16 is 2, I'm going to have 4 squared, which is equal to 16. And again, I can check the original question in my calculator like that. Okay, so notice that I had an exponent with a base of 4 and a log with a base of 4. They're the same base. Now, the inverse of exponentiation, so the inverse of taking the exponent of something, is taking the log. They undo each other. So it shouldn't be that much of a surprise that we just end up with 16 because they have the same base and inverses undo each other. So here it is formally stated. Logs and exponents are inverses of one another. So since the base of the exponent and the base of the log are the same base, it only works when they're the same base. The inverses cancel each other out and you're only left with the argument. So this is a cute little shortcut that you can use. It's not on your formula sheet, but it's definitely worth remembering. If you have a base and a log with the base that are the same, and the log is the exponents and the logs undo each other, and you're just left with the argument. Okay, let's try another one here. So this one here, we're going to combine two different logs, and we're going to then subtract them. Okay, so let's look at log base a half of 1/8. So I'm really asking myself, 1/2 to what exponent is 1/8? Now the reason that I don't leave these or don't change these to whole numbers is because they are both fractions. So if they are both fractions, we can just leave them as a fraction. When I don't do that is, for example, in the next one, when I have log base a half and 8. So if they're a fraction and a whole number, I always go with the whole number. So 1/2 to what exponent is equal to 1/8? So just like I did before, I can list my powers, but this time they're powers of a half. So you can see that 1/2 to the exponent of 3 is equal to 1/8. So that means that log base a half of 1/8 is just 3. Okay, so let's look at the second part here. So because I have a fraction base and a whole number argument, I'm only focused on the whole numbers. So 2 to what exponent is 8? So I can go to my powers of 2. So 2 to the exponent of 3 is equal to 8. Now because I have fraction base and a whole number answer, I know that my exponent has to be negative. So that means that log base a half of 8 is just -3. So now that I've figured out my two individual values of the logs, I can now subtract them. So log base a half of 8 is 3 minus log base a half of, sorry, let me say that again. I said the first one wrong. Log base a half of 1/8 is 3, and then log base a half of 8 is just -3. And 3 take away -3 is 6. So this one here, we can put the original question into our calculator just to check if we did it right, and we did. So I know you can put all of these into your calculator, but learning the steps of how to do logs is really important because sometimes you'll encounter questions that don't use numbers, they use letters. So that's why we're going through all of the steps. Okay, so you've seen that we can evaluate logs on the calculator because I'm always checking on the calculator. So I want to talk to you about a common log. So on your calculator, you have a log key, and I'll show you on the calculator where that is. So if I just go into my calculator here. Okay, so if you look at your calculator right here to the left of the number 7 on your calculator, that's where your log key is. Okay, so it's to the left of the number 7. So that log button is just a common log, and what it means is it has an invisible base of 10. So if I plug in log of any number, it's like saying log base 10 of any number. Okay, so if we want to evaluate numbers just using common log, we can do this in two different ways. So we're going to doing it algebraically without the calculator, and then we're going to use the log key on our calculator just to see if it actually works, because so far we've been practicing what we do here. So if I have log of 1,000 and I want to convert it into exponential form, okay, so log of 1,000 is the same as saying log base 10 of 1,000. So I just ask myself, 10 to what exponent gives me 1,000? So a neat little rule happens with tens, powers of tens, because they're zeros. See, it's 10 to the exponent of what? You just count how many zeros there are, and that's 3. So it's 10 cubed equals 1,000. So that means that log base 10 of 1,000 is 3, and I can even just say that log of 1,000 equals 3. Now I can also use the log key on my calculator just to evaluate it, and I can see that it does in fact equal 3. So you can always use that log key if you have a common base of 10. Now we're not going to do natural logs at all. The only time we ever use natural logs is when we do a regression. So don't worry about that. Okay, so let's try these ones here. We're going to evaluate logarithms by changing the base. Okay, so if I asked you to evaluate log base 5 of 50, what problem do we encounter? Well, let's use what we've been doing about logs. 50 is not a power of 5, because normally I would ask myself 5 to what exponent gives me 50? And you can see using my table of values there, my powers of 5, 50 is not one of the powers of 5. So we have to see where it is approximately. So I know that 5 squared is 25, and I also know that 5 cubed is 125. So that means that log base 5 of 50 is going to be in between 2 and 3. So 5 to some exponent is going to be 50. It's going to be between 2 and 3. It's probably going to be a lot closer to 2. So the answer to this one is it's going to be between 2 and 3. So we can't do it with exponential form, but what we can do is write it as change of base. So here's what we're going to do. So we're going to evaluate log base 5 of 25, just converting it to exponential form. So we're going to ask ourselves 5 to what exponent is 25? So we go to our powers of 5, and I can see that 5 squared is 25. So that means that log base 5 of 25 is 2. Now I want you to put into your calculator log of 25 divided by log of 5. So if I put that into my calculator, look what I get. I also get 2. They're the same. Okay, so since they're the same, I can say that log base 5 of 25 is the same as log of 25 divided by log of 5. And that's to say log of the argument divided by log of the base. Let's try this again. So if I have log base 3 of 243, I want to convert it to exponential form first. So I'm going to ask myself, 3 to what exponent is 243? So I go to my powers of 3 again, and there it is. So I know that 3 exponent 5 is 243. So that means that log base 3 of 243 is 5. Again, let's put it on the calculator. Log of 243 divided by log of 3. Putting that into my calculator, I also get 5. So again, this is further proof. Log base 3 of 243 is the same as log of 243, which is log of the argument, divided by log of 3, which is log of the base. So that's 2 examples where we're seeing that this method works. So change of base identity is something that we can use to evaluate logs on our calculator. So if I have log base 2 of 8, I want to write it in a form that I can plug it into the calculator. So I'm going to take log of my argument divided by log of my base. Now, we already know that the answer is 3 because we learned that in the last lesson. Let's check if it works here. And it does. Log of 8 divided by log of 2 is 3. Okay, let's try this next one. Log base 2 of 64. To evaluate it on the calculator, I can do log of the argument divided by log of the base. So let's try that. And we get an answer of 6. And I know that's right because 2 to the exponent of 6 is equal to 64. So it looks like we have a method that we can put these logs into the calculator when they don't have a base of 10. So this is called the change of base identity. So log base b of x is the same as log of x, log of the argument, divided by log of b, log of the base. Okay, so as an example here, log base 4 of 1024 can be evaluated by converting to a base of 10 because these ones here don't have a base stated. So there's an invisible base of 10. So this change of base identity is how the TI-83 calculators evaluate their logs. Okay, now I know TI-83s, you don't have a fraction key, so actually a little bit more accurate way of writing that would be this: log of 1024 divided by log of 4. So that's how my 83s are going to enter it in. 84s and the color calculators have a bit of a shortcut. Okay, so all you have to do is enter in math, alpha math, and you get this little log template. Let me just show you on your calculator what that would look like. So if I were to go out on my main screen, I'm just going to hit math, alpha, math. And you see, you get that little log template. Then you can put in any base you want, and if you toggle over it, you can put in any argument you want. So that's how the 84s do it. But this change of base is how the 83s put it into their calculator. Okay? So if I wanted to practice this using change of base, just practicing that idea, to enter in log base 4 of 1024, I would do log of 1024 divided by log of 4. To do this one here, I have to do 3 times the log. And be careful because we have a fraction here, so we have to be careful with our bracket placement. So if I wanted to use change of base, I would say 3 times log of 1 over 1,000 divided by log of 2. Okay, here, 6 to the exponent of log base 6 of 216. So I would enter that in as 6 to the exponent of log base 6 of 216, or using change of base, I could do 6 to the exponent of log of 216 divided by log of 6. Now, this looks like that law that we looked at. If we have a base of 6 and a log has a base of 6, isn't that the matching law? Because this base and the base of the log are the same, so they could just cancel to be 216. So we could use that canceling shortcut as well. Okay, for this one, log base 2 of the root of 1 over 1024. We can enter it in like that, or using the change of base, I can say that log of the root 1 over 1024 is divided by log of 2. You can do that, and you would also get the answer of -5. Okay? Okay, so let's look at this one here. This is where it's really useful using that change of base, is to put log functions into our graphing calculator. So if I have the function f of x equals log base 7 of x, if I want to use a graphing calculator to produce that graph, it's going to go in my y equals. So in my y equals, I'm either going to enter it in as log base 7 of x, if I have an 84, or log of the argument divided by log of the base if I have an 83. So both these methods will produce the same graph. And this is what the graph would look like. Now, on your graph here, you might not have this part here. I added that in. It almost looks like the graph stops. Let's just look at that on our graphing calculator, actually. So I'm going to go into my graphing calculator and clear out what I was working on. I'm going to go math alpha math. And I'm going to put in, it was log base 7 of x, yes. Okay, so I'm going to go into here and I'm going to go log base 7 of x. And I just want to show you what it looks like. I fixed my graph up, so I just want to show you what it looks like before I fixed it up. That's what it looked like. So it kind of looks like it stops right there. And it doesn't stop right there. It continues to go down and it hugs the y-axis. The reason that it stops there is just a pixelation issue. So it's just the pixelation with the calculator. So I want you to know that it does continue to go down. So that's why I kind of added that onto my graph. Okay, so if I wanted to graph the following equations on my calculator to solve them, if I have log base 7 of x equals to 5, so here's what I can do is the intersect method. So I can do the left side in y1, the right side in y2, and I had to adjust my windows because the x value was quite big. So I had to play around with it. So that's the window that I used. And then I can do my second trace, calculate, option number 5 for intersect, and I get that my solution to this equation is 16,807. Okay, on this one here, see how it's set to 0? On this one here, I can also use y1, y2 intersect, but in y2 I just put in 0. Okay, so there's my equation, there's 0, and I look where they intersect. Again, I also had to adjust my window, because remember, if you cannot see your point of intersection, you can't calculate it. So you just have to keep adjusting your window until you find a window setting that works. Okay, let's just review here how we can solve these equations by converting them to exponential form. So if I have log base 7 of x equals to 5, I'm going to use my circle of logs. So it's going to be 7 to the exponent of 5 equals to x. So I'll just put that into my calculator, 7 to the exponent of 5. Oh, is my calculator not going to work for me here? Oh, there we go. So 7 to the exponent of 5. And I get an answer of 16,807. Okay, so that's another way you can do it. We've seen it graphically, and now we see it algebraically. Now, this one here that we did, we can't just put that into exponential form as it stands. We have to isolate the log first. So let's look at the steps to do that. So I will add 9 to both sides. That's gone, and I get 9 equals 3 log base 7 of x. And then I will divide both sides by 3. That's gone, and I get 3 equals log base 7 of x. And then I can use my circle of logs. So you always have to isolate your log first before you can do circle of logs. Okay, so, let me flip that over. I'm going to do 7 to the exponent of 3, and that will equal to x. So 7 to the exponent of 3 equals x. I can put that in my calculator, and I should get 343, which is what I got on the last one. Yes, perfect. Okay, so a couple different ways that you can go through and solve, graphically or switching to exponential form. So to summarize here, the value of a log is the exponent the base is raised to get the argument. When the base and the argument match, that matching law, the log has a value of 1. And remember that canceling law. When you have an exponent with a base of b and you're raising it to a log with a base of b, they cancel to be just the argument. So this concludes our lesson on musical wood. Why would I say this is musical wood? Because logs have rhythm. So I want you guys to work on your assignment. Please make note of the omitted questions for C and D. Hope this lesson helped, and I'll see you for the next one, 5.4.